First of all, I want to thank the organizers for inviting me to present this result. It's a result I got with Konstantinos Manos and Miriam Weilemann. You can find some primitive version here. We'll try to get a new version this week, hopefully on Wednesday. So I recommend you not to get into this because it's a bit badly written. Okay. Damn it. Okay. So as some of you know, I've made a career by contemplating this kind of quantum information processing scenarios in which you have several separate labs that are conducting measurements, right? I mean, and on some local Hilbert spaces, no? That's boring, but it becomes interesting when you abstract everything and you make it device independent, and then you regard each lab as a black box with an input port and an output port. And then you get a multivariate Bell experiment. So the only thing that you get out of these experiments are the what we call the correlations or the boxes. In this case, let me call them space-like correlations. Okay, it will make sense because of what is coming next. And I think it's very interesting to study these correlations. I'm going to give you two reasons. Well, my personal motivation is quantum foundations. If you manage to characterize quantum correlations or quantum spatial correlations, or at least bound them, then you're answering the question, how can things look like? Because each of these correlations is like a picture of how reality looks like. And why is this important? Well, once you know how things are, then you can also work out when they are not what they should be, right? I mean, hopefully, maybe this could happen, right? I mean, that we do an experiment that actually is not doesn't follow the laws of quantum mechanics. How will we know? Well, if we had a characterization even from the outset of a set of quantum correlations, then we could know, and we could even devise some criterion to falsify quantum mechanics. And there was a reason why I got into non-locality in the first place. But also there are some practical applications. No? If you buy into quantum mechanics, you can say, well, if I have a bound on a set of quantum correlations, I can use it to derive device-independent quantum key distribution results or results in device-independent random certification. So I think it's very well motivated to investigate this, to investigate space-like correlations. However, most experiments in quantum mechanics take place at a single lab. Okay. And in those experiments, you have a system, a quantum system that you're trying to isolate from the environment. At some point, you will measure it, otherwise you won't get experimental results. And very often, the measurement destroys the quantum system. Okay, it's a demolition measurement. These are the measurements I will consider in this talk. And sometimes, actually very often, one can choose when to conduct the measurement. So if I were to abstract this standard experiment in quantum mechanics, I would think of something like this. You have a system, a quantum system, in the lab that you represent with a Hilbert space. You can probe it in some ways, and this will give you some experimental results. And next to the system, there is a timer. And you can use the timer to decide and also to record when you're conducting the measurement. Now, if we assume that the system is approximately closed, then its dynamics will be given by some time-independent Hamiltonian. Wait, I don't get, yeah, okay. Time-independent Hamiltonian. And I will model the measurement with a period that will not depend on time, okay? All the dependence on time, I'm going to put it on the state. Can you see the cursor? Because I can hardly see it. No? Yeah. Okay, well, tough. Maybe I can do something here. Can you see? Yeah, okay. Well, okay, it's not ideal. It's not ideal because there's a delay. Well, let's try to see what I can do. Okay. Okay, well, you apply the bound rule, right? I mean, and then you get the standard probabilities. Now, let's make everything interesting. Let's make everything device independent. And what you get is a set of correlations that, in this case, I will call it a timeline. The timeline is simply the probability of obtaining the result A when I conduct measurement X at time T. And this is the kind of objects that I want to characterize. Now, you may wonder why, no? What is the motivation, right? I mean, or is there a motivation? Maybe there's not a motivation. I'll tell you first my motivation. My motivation is again from quantum foundations, because if spatial correlations tell you more or less a picture of reality, this thing give you a movie. So if you can manage to characterize or bound these correlations, in a sense you're answering the questions, how can things change in a quantum theory? So this is the reason why I think it's interesting. Now, why is this relevant for quantum foundations? Well, there are some boring people who think that everything is quantum. And some of these people who work in these fields, right? I mean, they believe that gravity is also quantum. In this picture, we have two massive particles that are quantum, and they're interacting through a quantum field. Everything is quantum. Because everything is quantum, then it is subject to quantum dynamical constraints, the ones that I want to characterize. But now there are some other people who are a bit more creative, and they have proposed actually some concrete models, no? In which gravity is classical. And in this picture, not everything is quantum, because it's not quantum. It doesn't have to satisfy the constraints or the bounds that I'm going to show you, that I'm going to derive. So maybe if reality is a bit more like this, one could devise an experiment to refute all these models. It would be really cool. Now, more practical. More practical application is that some colleagues of mine from ICOKI, Vienna, they have considered these kind of scenarios, these time demolition measurement scenarios, in order to generate randomness, no? or to certify randomness. This picture is a bit misleading because you may think that they're measuring at times T1 and T2. No. You measure either at time T1 or at time T2. These are demolition measurements. But they show that making some assumption on the energy of the system inside the boxes, and they can certify that the numbers that the boxes are producing are random. Okay, so if one managed to characterize this set of correlations better, then one could extend these protocols and to more than two measurement settings, two measurement times and more measurement settings, maybe more outcomes. Okay, so this is the setup, and this is what I want to characterize. No? So what are the set of possible quantum correlations that you can get in this scenario? And then we bump into the first difficulty, because the set is unbounded. Okay, so if you don't make any constraint on the realization, the physical realization that is producing these correlations, then you find that the set of data sets are like timelines, but only for a finite number of times. So the measurement statistics have a finite number of times. You find that there's really no constraint. However, decades of research in quantum speed limits have taught us that the picture changes when you constrain the energy of the system here. Then you get something that is non-trivial. So this is what I'm going to do now. I'm going to start speaking about energy constraints, because there are many energy constraints that have appeared in the literature, and they are inequivalent, which is good, right? I mean, because each of them targets a different experimental scenario. Okay, in many experiments, it's natural to consider what I call the spectral constraint, in which you know what the energy levels are. Okay, you know the energy levels, and there are fairly many. You find what is very natural, at least in these architectures, in which it is easy to prepare some state in a linear superposition of different energy eigenstates with known energies. It appears in one of these papers about randomness certification, exactly this kind of constraints. And consider this constraint and suppose that this particular case in which, or pathological case in which there are lots of levels and they're very, very close to each other. Well, in that case, what you could do is to make this approximation to suppose that the Hamiltonian is continuous. And the only thing that you're assuming is that if you try to measure the energy of the system, you'll get a number between 0 and E+. So this I call the hard energy support constraint. I call it energy support constraint because this is the same as leaving the Hamiltonian alone and making a constraint on the support of the energy density of the state. Okay, and I call it hard because this is a soft one, but I don't have time to speak about that one. This has appeared in the literature of quantum speed limits, and also, yeah, once you consider the continuous Hamiltonians, it also makes sense to speak about the average energy constraint. Okay, in which case you only put some bound, some upper bound on the average energy of the system. This is very suited for this kind of experiments because with Rabi spectroscopy you can estimate this number, not without much complication. And it has appeared in the literature of quantum speed limits. Actually, the second paper on quantum speed limits used this constraint. And now this one, which is the most famous one, and to be honest, I don't understand why. Okay, but I'm telling you. So this is the most famous one, right? I mean, it's a constraint on the energy variance of the system. This is also more or less natural in this kind of architectures because, again, you can estimate this number easily using Rabi spectroscopy. Now, it's very popular. It has appeared in the literature of quantum speed limits. The first paper in quantum speed limits used exactly this constraint. It has appeared over and over in literature on resource theories, and also in this other randomness certification paper. Okay, so for some reason, people like this set a lot. Okay, so okay, let's consider it. Once you impose this constraint, you get a different set of correlations. Okay, so the first question that we tackle in the paper is how to characterize them, how to characterize this set of correlations. And in this sense, we're really lucky because for spectral constraints, that is, when you know what the energy values are, energy levels are, then the set of correlations, the set of timelines that you can generate are SDP representable. All the functions that you can express like this, where here you have some variables. These are supposedly semi-infinite variables, and the rest of it is just a constant. And that's quite convenient it allows you to solve a problem that you would think is unrelated. No? Suppose that you want to decide an optimal atomic clock, or more like a stopwatch. So somebody comes to you with this spectrum and says, well, what is the best clock I can make with this system? Well, the question in mathematics is this one. Find me a P of EM and a state such that the timeline generated with this Hamiltonian, we're starting with this state and this P of EM, minimizes in 2 norm some reference timeline. For example, that of a perfect clock. Well, this problem is an SDP. You can solve it efficiently. Okay, so it's something cool. As a physicist, I'm very happy to find out that some physically relevant problem is easy to solve. If I were a computer scientist, probably would think the opposite, no? Because I think, well, what a boring thing, no? But okay. Okay, how about the others, right? How about the other constraints? Well, for the others, I don't think they are SDP representable, but for sure, I can give you a characterization through hierarchies of semi-definite programming relaxations. And how do they look like? Well, I'm not going to show you because it's a bit of a pain, but the index of the relaxation is proportional to the size of the SDP matrices, meaning that in a normal computer, you can go to index m equals 200. And we also have bounds on the speed of convergence. So if you put everything together and consider the complexity of solving an SDP, what you find is that you want to characterize any of these sets up to precision delta. You can do it in time polynomial on 1 over delta and the number of points that you get in the data set. So it's a problem you can solve efficiently. And this is a surprise. Well, at least it was a surprise for me. Okay, I'm going to talk about something else. I'll talk about self-testing. So I think I've argued that the data that you get in an experiment gives you some information about the energy distribution of the state. And the question is whether it could be that some data sets could tell you everything, could tell you what the state, what the system is, what the state is, the state that you prepare at the beginning, what the Hamiltonian, and what the PVM elements that you're applying are. Okay, so we have to do is to generalize the definition of self-testing. No? In this scenario, would be a self-testing, a finite set of measurement statistics, self-tests a given realization under some energy constraint. If for all realizations that fit the data set, you can find some isometry such that this thing is the evolved state times some PVM element. We use sandwiches with the isometry. You get exactly the same expression, but in terms of the reference operators, tensor some Young state. And now there's something very curious about this formula. There's something very curious. There's something that is not curious at all in spatial correlations, but I think it's kind of interesting, right? In time correlations, which is that this part here does not depend on time. It's weird, right? I mean, because according to this equation, I don't have access to these degrees of freedom. My system is just probing this. So how can I be certain that this part is not evolving in time? Well, it's because we're in quantum mechanics. And in quantum mechanics, to move things, you need energy. So what happens in a self-testing statement in these scenarios is that all the energies is being used to move this degree of freedom. So there's no energy left to move the others, despite the fact that we don't know what they are. Well, you can extend this definition to more, to make it robots, right? I mean, to put some, in the case that you don't have a complete fit, but you have a fit up to precision delta of the data set that you consider. And then results. So under the hard energy support constraint, that is assuming that whenever you measure the energies between 0 and E+, then this 2-point data set, these are the 2 points, this one and this one, it properly self-tests radio oscillations. The price is not that very impressive. So let's go to, because, okay, qubits are for losers, no? But this is a Q-trip, no? You can also self-test a Q-trip with this 3-point data set. Yeah, Q-trits are almost a qubit, no? Let's go to Q-quartz, no? Q-quartz, I can also give you something, right? And probably you get the progression. If I give you this n-point data set, then you will be properly self-testing what we call the n-dimensional quantum clock. We call it like that because it's kind of a clock, no? If you measure at this time, you will get 0 with probability 1, but at these other times, you always get any other outcome, no? Okay, so far, I've been just mirroring results in space-like correlations. So in space-like correlations, we can characterize the set of quantum correlations through hierarchies of SDPs, partially. And in the time-like case, we can do the same, right? I mean, and the concept of self-testing was born. It's actually an invention of Sidelson in this scenario, and then we translated it to this other scenario. Now I want to speak about something different. It's a problem that it does not have a natural formulation or in the space-like situation. It's something that's really special for time-like correlations. This is the problem of extrapolating measurement data. Okay, so the problem is very easy. So suppose that I give you some noisy data set. It's like a data set, but also with error bars. And I give you some extrapolation time and some objective function. So the question is, find the possible values that this function can take over all timelines that comply with some energy constraint that fit the data set, the noisy data set. Okay, so this question from the point of view of quantum foundations is answering the question, well, what is going to happen? Which is, again, goes beyond foundations. I would say it goes beyond philosophy, right? I mean, so that's why I'm interested. No, I want to know what's going to happen. This is a practical reason to study this, which is this. When you try to evolve or to model the evolution of many-body quantum systems, normally you cannot do it exactly because it's a very complicated problem. So you use numerical methods, and some of them allow you to give you upper and lower bounds on the average value of some physical quantity a long time. But what happens is that at some point they break. And they become completely useless. No? This is what happens when you use MPS approximations. I have a paper with Mateus Araujo. We provide a similar method using SDP relaxation, but we have exactly the same problem, right? I mean, the bounds are really, really good for some time, and up to some time, they just become useless. So for these scenarios, it would be really cool to have some high-level extrapolation techniques that take in the data that we know that is reliable, allow us to extend this region of predictability a little bit. So that's the motivation. Okay, so what is this extrapolation problem? At its core, it's a double optimization problem. You want to maximize this function over all possible data sets that belong to one of these sets, and also minimize it. And then the answer will be between these two values. Now, these optimizations in general probably are difficult, maybe even undecidable. But what I suggest to you to do is simply to do an SDP relaxation. You optimize over the SDP approximation. And then, of course, because you're optimizing over a bigger set, you get a larger interval, which is fine because it's sound. So if an experimentalist comes to me with these things, with this data, then I can tell the experimentalist, look, at this time, you will observe something between these two values. And it will be right. It will be a sound prediction. And if you're not satisfied with the prediction, then you can make it as close as possible to optimal in the limit when you have infinitely many computational resources. Okay, now there's another question that it seems related, but it's not, right? I mean, which is the fact that you can solve the extrapolation problem doesn't mean that you can extrapolate the behavior of a system, because it could be that most systems do not allow you to extrapolate their behavior, right? This is what I want to tackle next, right? I mean, given a system, can I say something non-trivial? Okay, so I'm going to use this hard energy support constraint. And under this constraint, you can see that some physical systems are very easy to extrapolate, in the sense that they need few data points with reasonable statistical precision. And one of these systems we already saw is the n-dimensional quantum clock. And what is a spin-off of this self-esteem result is that if you manage to, you have a noisy data set with noise, the inverse of some polynomial on tau, then you will be able to make a non-trivial prediction at time tau. Okay, so with only n data points, which is really good, right? I mean, it means that you can make long-term predictions if you wish. Also, another thing is that under this constraint, all quantum systems can be extrapolated as long as you have enough data points and also enough precision. And the reason is very simple. Let's go to an idealist scenario where I give you a region, an interval with no noise, no? Well, because of this constraint, this function is analytic, and because I gave you the value of the function of some interval, you can extrapolate it, right? Of course, right? I mean, by analytic continuation. Now, this is not realistic because, of course, you never have infinitely many points and zero noise. But what happens when you have a lot of points and very, very little noise? Well, this is the problem of extrapolating an analytic function given noisy samples, and this is a problem that people have considered before in in computer science. And they have methods to to do it that give you some rigorous bounds, and the bounds go to zero. I mean, the interval or the confidence interval, the width goes to zero as you increase these two numbers. No, so increase this one and decrease this one. So in principle, you can extrapolate whatever you like. There are bad news. There are bad news. There are bad news. Yes, they're very bad news. I agree. Yeah. The bad news is this. Think of this system. This is the most boring system that I can think of. You prepare a maximally mixed state. You have no Hamiltonian, and you measure sigma z. It is boring because the data set that you generate is just 1/2. It's really, really boring. So how difficult must be to extrapolate this? It doesn't do anything. It's always the same, right? I mean, but of course it's going to be 1/2, right? I mean, how? Well, let's try to find out. Well, if I just give me the system and then I start playing with the box, then what I can do is perhaps estimate n data points with some precision. And the question is what kind of prediction I can make for some extrapolation time tau. Okay, of course, if the number of points goes to infinity and the resolution goes to 0, then you will get that delta prime is equal to 0 too. And the question is what happens in the limit when you have lots of data points, but you have a bit of noise. Okay, well, how difficult it is to make an extrapolation with this system. It's really the most boring system in the world. And what we find is that delta has to be bounded by 1 over some super exponential function on tau. So if I give you this boring data system, you won't be able to make long-term predictions. It's impossible. You will need it's impossible. You need to do too many preparations. So this is the status of the problem now. There are some systems that are unproblematic to extrapolate and some that are extremely problematic. And I don't have any a priori rule to tell you one from the other, apart from trying to solve the problem. Okay, now for the last part of the talk, I'm going to speak about extrapolation phenomena, right? What is the weirdest thing that could happen when you're trying to extrapolate something? Okay, we discovered two things, actually. One, we call it aha data sets. Suppose that some experimentalist comes to me with this data set and asks me, Miguel, make a prediction for time tau. And I find that I cannot. Suppose that I find that for any data point that you can think of, I can find some timeline that fits perfectly the data set and predicts exactly the data point. This is what we call an Knightian uncertainty. It means that you cannot predict anything here. Okay, okay, this could happen. So I tell this to the experimentalist, and the experimentalist goes back to the lab, makes more experiments, and comes back with a second data set. And he explains me, look, Miguel, this was the data set that I got when I measured property 0, and here I'm measuring property 1. Does this help you? It's like, okay, what is the relation between 0 and 1? I don't know. Okay, you would think, well, of course it doesn't help me, no? How can this help me make a prediction here, right? I mean, I don't know the relation between these two things. But the problem is different, because now I'm looking for some timeline that fits all the data set, no? Not only these points, but also these other points. And it could be, in principle, that now that I have this extra information, I can tell with full certainty what will happen here. This is hypothetical, okay? But if this happened, then we will call this an aha data set. Okay, this is an aha data set for this data set here. Okay, so let's, I'm going to give you now an example of aha data set. Okay, aha data set is this one. It's a 3-point data set. I'm assuming the hard energy support constraint. And this data set is feasible. You can realize it with this three-dimensional system. And it has the problem that if you consider each of these data sets separately, you can find a 4-dimensional realization that predicts probability 0 here, another one that predicts probability 0 here. So this means that if I play with convex combination of these two realizations, I can get whatever probability here. So this means that I have an Knightian uncertainty at this time, at these two times. Okay, I have an Knightian uncertainty. However, if you take into account the whole data sets, we can predict that actually the probability of getting the results 1 at time tau is equal to 1. Here you have a data set. But it's very curious. It means that this data set is an aha data set for this one, because without this one, you couldn't make predictions with this one. And this one is also an aha data set for this other one. Yeah, aha data sets for each other. It's a sort of activation result. Okay, this is phenomenon 1. Phenomenon 1 was aha data sets. Phenomenon 2 is what we call fog banks. Again, the starting point is the same. Some experimentalist comes to me with some data set, and asks me to make a prediction. I cannot because there's an Knightian uncertainty. Now, you may think, well, what will happen after this time? Could I make a prediction after time tau? And intuitively, I would say no. I would expect to get a Knightian wall. I expect that if I cannot say anything at this time, I won't be able to make a prediction at any future time. And I say intuitively because my intuition is the intuition of a 4-year-old kid. So I imagine that because I know this data, I am here, okay? And I'm here trying to look to the horizon. So if this thing is already covered, right? I mean, if I cannot see beyond that, of course, I won't be able to see at future times. So this is where my intuition comes from. However, it could be in principle that you have this situation. You have a full uncertainty here, and then sometime later, full certainty. Sometime later, you can predict exactly what's going to happen. Well, if this happens, then we will say that the data set has a fog bank at time tau. And the intuition again is that, yes, there's fog here, and that's why I was not able to see what was going on here, but I can see what is going on at some future time because I'm in a really, really big mast, okay? Now, does this exist? Okay, I have to go to a more complicated scenario where you have one measurement but 3 outcomes. Because you have 3 outcomes, I need 2 plots to plot the distribution, right? I mean, I need probability of 1 and probability of obtaining the result 2. Again, it's a 3-point data set. Okay, so what happens is that you can generate it, right? I mean, it's feasible. You can. It's a 4-dimensional realization, and the problem is it admits some other 4-dimensional realizations that predict completely different things. Okay, actually, look at this, right? I mean, they're predicting opposite things at this time, tau 1. Okay, so what we have is an Einstein uncertainty here. If you start taking convex combinations, you can get whatever distribution here. You can make predictions here. Okay, but note that these 3 curves, they converge to some value, no? They all predict that if I measure at time tau 2, this measurement, then I will get a result 2 with probability 1. Well, we prove that this happens in general. Any curves that fit this 3-point data set will have these properties. Actually, you have a full certainty here. So you have a fog bank. Okay, now you may wonder what happens, because I was always assuming that you have the perfect data set. If you allow a bit of noise, what happens is that you still keep the fog bank at time tau 1, but now at time tau 2, you don't have full certainty, you have almost full certainty. So all the results that I'm talking about are robust. Okay, so I'm going to, let's make a summary, shall we? Okay, so I hope to have convinced you that time demolition measurements is a rich and explored framework. We have the luck that all the sets that we thought of had an efficient representation, except these 2. I didn't have time to talk about them, which breaks my heart. We've also seen that it has self-setting data sets, like in the space-like correlations, and also, I think, very surprising extrapolation effects, like the Affa effect and the fog bank effect. Now, for the future, what could we do? I think it would be interesting to study extrapolation in another scenario that people have considered in the literature called the temporal correlation scenarios, in which you don't have demolition measurements. You can measure afterwards, and then what you get is a string of bits or a string of results. And then in this case, I think it's very interesting to try to predict what's going to be the next outcome. And of course, another possibility is try to explore this idea that I told you of trying to, through a characterization of this set and through some suitable energy constraints, to try to propose an experiment to refute this class of models for quantum gravity. I'm going to stop here. Thank you very much.
Thank you very much for the very nice talk, Miguel. Do we have any questions?
So can you have a non-commutative version of the theory in the following sense? So your SDP doesn't know about time. All you tell it is that 2 labels of these correlators are related by a representation of a one-dimensional group, and you constrain the ERAPs that occur by your energy constraints. No, but you could also have a rotation scenario where they're labeled by theta and phi Euler angles or something. Would that work?
Yeah, I've been thinking about that. I have to think more, because actually Marcus Muller is very interested in that. Yeah, no. He has the papers that I showed you before. Originally stem from because he wanted to characterize the set of rotations, but then he only characterized rotations through one angle, and that's why you get in the end Hamiltonian. But it's a good question. No. I think it's more complicated for sure.
Questions? I will be fast.
Thanks for the nice talk. I was wondering what's the intuition for the AHA data sets you showed. It looked like the 3-box paradox, but I didn't have time to see.
Okay, I don't know the 3-box paradox, so I cannot comment on that, but I can tell you, the intuition, I can tell you why we know that you can make a prediction, maybe. Up. Yes. No. Okay, yes. Oh, yes. Yes, what we show is that the only way to have these two data sets, okay, these data sets actually, okay, they tell you some information. They tell you that the state at time tau 1 is orthogonal to the state at tau 0 because you can distinguish them with this measurement. Okay? They tell you that the state at time 0 you can distinguish from the state at tau 2 because of this other measurement, no? So you know some orthogonality relations. Well, for the self-testing result, we proved some result that if for these spacings and under the hard energy support constraint, if the states are become orthogonal, then you can single out what is the energy density of the state, and you find that it's peaked in only 3 parts. And what you find essentially is that the system is because of this distribution, the system is periodic. So what happens is that this implies that the period is exactly this. So you know that the polarity here is going to be the same as here because you have the same state. And for the case of the fog bank, it was more or less the same idea. We also proved the system is periodic. So actually, the fog bank is cool because you have an net uncertainty, full certainty. Net uncertainty, full certainty. It goes forever and ever because it's a periodic system.
Okay, thanks, Miguel. My question was related to the self-testing that you talked very briefly, because in non-locality, we always need to have non-commutativity on both sides to prove the results. But here you have one measurement and one Hamiltonian. So I'm wondering what is
I have an energy constraint. Without the energy constraint, I wouldn't be able to do anything.
And this basically...
That's enough, no? Okay, yeah. It's a bit of magic, no? But it's related to this thing of... At the core is the thing that I just explained, all right? I mean, if you can prove that things become orthogonal because of the evolution of the Hamiltonian, and the Hamiltonian is bounded, then you can say just very, very quickly start saying things about the Hamiltonian. You know that it's discrete or effectively discrete and lots of things, no? And also because of the format they have, right? I mean, you have a result 1 and then 0, then you can work out what that it has to be an eigenstate of the POVM elements, no? So you start working with that and you get the result.
Maybe a last question. Okay, don't see no one. Okay, so let's thank Miguel again.